No.
Okay, well, we're very happy to have Ben Safdi coming to us from all the way from Berkeley. Ben got his PhD from Princeton. He was a postdoc at MIT, where he was one of the co-proposers of the abracadabra Axion search experiment. He's made his way slowly from very theoretical physics to more and more experimental physics. He then went on to a faculty position at Michigan and is now at Berkeley. So we're very happy to have him telling us about how to find axion dark matter with radio telescopes.
Hey, well, thank you for the introduction, and thanks for the invitation to speak here. It's a shame that I can't be there in person, especially now that I'm so close by, but hopefully this can be the first of many encounters, and I look forward to seeing you all in person, hopefully at some point soon. So I'm going to tell you today about some recent work of mine over the past few years on looking for axion dark matter with radio telescopes. So first, just to get everyone on the same page, this is a picture of a galaxy. This is not a real picture. This is a snapshot of a simulation. And this also isn't the ordinary matter. If you looked at the ordinary part of this galaxy, it would just be some tiny thing in the middle. And what we know today is that most of galaxies like our own Milky Way are composed of dark matter, and both by mass and by volume. And the big question that I'm trying to figure out, and other people are, is what is this stuff? And that's going to be the subject of this talk today. The first, perhaps precise estimate of the amount of dark matter in systems like our own Milky Way came from Vera Rubin and collaborators who measured the rotation curve of stars within and gas within the Milky Way. I'm showing you a modern image here of the rotation curve for the Milky Way. The circular velocity of the stars is measured by Gaia, are shown here on the y-axis. The black data points is a function of the distance away from the galactic center on the x-axis. In order to explain the data, you need to have a dark matter component. The dark matter contribution is shown here in orange. And from this, you can extract a modern estimate of the local dark matter density of about 0.01 solar masses per parsec cubed. Actually, I think my own small contribution to this quantification of the amount of dark matter in our galaxy is to make perhaps the most local measurement of the dark matter in the solar neighborhood in a box of about 100 parsec cubes. This is in a paper of mine from a few years ago where we were actually looking for something else. We were looking for something called the dark disk. We didn't find it, but in the process, we measured the local dark matter density. And we did so by looking at the vertical velocity dispersion of stars about the galactic plane. And assuming that the system of stars was in equilibrium, so there are tracers of the gravitational potential, and then imposing something like the virial theorem, which allows you to relate the average kinetic motion to the gravitational potential, which is sourced by matter. To go beyond this in measuring the local dark matter density, there's an issue, which is that one of the key assumptions in this analysis, and analyses like it, is the assumption of equilibrium, which we know is violated for the Milky Way. So one thing that I've been working on recently, as have other people, is in using stellar accelerations instead of velocities measured by by acceleration surveys and instruments like Gaia, because by looking at accelerations, you can measure in principle densities without having to make assumptions about equilibrium. And so I think that's going to be an important line of research going into the future to nail down the uncertainties on the dark matter density. This is important for this talk because, and for laboratory searches for dark matter, because when you're looking for particle dark matter, in order to interpret the data that you acquire, both in the laboratory and in indirect searches, in order to interpret that data in the context of a particle physics model, you need to understand the astrophysics and you need to understand the amount of dark matter that's in the system. But the subject of the talk today is going to be, again, what is the microscopic nature of dark matter? How does dark matter, what does it look like on small scales as a particle? And how does it talk to the rest of the ordinary particles of nature that we know and love? And when you start asking questions about the microscopic nature of dark matter, it's pretty fascinating how little we know. For example, if you focus on one aspect of it, the mass of the particle, it could be anywhere from so small that the quantum wavelengths of the dark matter is the size of galaxies to the Planck scale. And if you allow yourself to talk about non-particle dark matter scenarios like black holes, you can keep on going up for many decades of orders of magnitude. And so what I've been doing over the past few years is just trying to probe different parts of this parameter space with different techniques to figure out how can we constrain this massive parameter space using astrophysical data or laboratory data sets or simulations. And today I'm going to be telling you in particular about astrophysical probes that could help us narrow down where we live on this complicated parameter space. And in particular, I'm going to be focusing on the Qcd Axion today for two reasons. One, it's just, I think, a very well-motivated dark matter candidate. And two, it's a big part of the research that I've been doing recently and then people in my group have been doing recently. So I have things to say about it. Okay, so let me now give a brief introduction to the Qcd Axion, just to get everyone on the same page before I talk about my work. So the Qcd Axion was originally introduced to solve the strong CP problem related to the absence of a neutron EDM. More precisely, there's a fundamental parameter of nature within the standard model called theta. And if theta is non-zero, there would be a neutron EDM, which means neutrons would precess in the presence of electric fields. If theta happened to be exactly zero, there would be no neutron EDM. And the strong CP problem is the observation that in nature, no neutron EDM has been observed, which puts a constraint on this theta parameter that says that it should be about 1 part in 10 billion away from zero. And you should think of this theta as an angle, which naturally would have taken values between minus pi to pi. So, so this looks strange. Why do we live so close to zero? So in the late 1970s, Pecci and Quinn postulated a solution to the strong CP problem, which is the axion. And what they noticed is that when you make your universe and you draw a value for this theta parameter, it looks like it wants to roll down to the origin. That is, the neutron would be in a lower energy configuration if this fundamental parameter of nature could go down to the origin. But of course, this doesn't make any sense because it's a fundamental parameter of nature. It can't evolve. So what they did was they promoted this parameter to a dynamical field, the axion field. And now this dynamical field can relax down to the origin, thus solving the strong CP problem. So more precisely, this theta parameter enters into QCD Lagrangian in the following way. G here is the QCD field strength, G tilde is its Hodge-Dual. And the axion field, you should think of it as a pseudo-Goldstone boson of a symmetry, which is broken at some high scale FA. And it enters into the standard model through this dimension 5 operator, AGG tilde. So there's a mass scale in the denominator, FA, that's the scale where the axion was born. It needs to be some high scale. Then the neutron EDM is proportional to this whole combination. Below the QCD confinement scale, QCD instantons generate a potential for the axion. And now when the axion minimizes this potential, it dynamically removes the neutron EDM, thus solving the strong CP problem. So now our axion went from being a Goldstone boson of a symmetry broken at the scale FA to a pseudo-Goldstone boson because QCD generated a potential for it. And if we expand out that potential, we'll find a small axion mass. For example, for a decay constant about 10 to the 12 GeV, you have a mass on the order of 10 microeV. And most importantly for this talk, axions are also expected to couple to electromagnetism through a very similar operator, a FF tilde, where F is now the QED field strength, or writing this out in terms of electric and magnetic fields as AE dot B. And GA gamma gamma here, this is again a dimension 5 operator, is a dimension full coupling that scales like 1 over FA, although there can be some model dependence which enters into the numerator. And by the way, please stop me if anything I'm saying is not clear. Okay, so that's the axion as a particle. What I want to do right now is just briefly review axions as a dark matter candidate And then I'll talk about work going on today to actually try to detect if this particle exists. So we use different language when we talk about axions as dark matter than when we talk, for example, about WEMP dark matter. And the reason is simply that axions have a really small mass if they exist. And what does this mean? What we measure in astrophysics, as I hinted at earlier in the talk, is the amount of mass within some fixed volume. And what that means is as we make the particle mass smaller and smaller, we need more particles within that volume to make up that fixed total mass. And what that means is that the wave functions of these particles are going to begin to overlap. These are axions or bosons, so they're allowed to do that. We're going to have a high occupancy numbers for each quantum state, and we're going to transition from the quantum regime to the classical regime. So when we talk about axion dark matter, the axions are so light that they work very safely within this classical regime. And it makes more sense to talk about axion dark matter as the evolution of classical fields than it does to talk about axions as a collection of individual particles. Okay, so now we have this new fundamental field of nature that we need to include in the equations of motion in our early universe in order to figure out what the abundance of dark matter is. So here are the homogeneous equations of motion for the axion field in the early universe. H here is Hubble, that's T squared over M Planck in the early universe. So I can solve, I've also neglected spatial gradients. I'm just looking at the homogeneous parts of the equations of motion. So I can solve this in real time in a high temperature limit, because at high temperatures, Hubble is going to dominate. I can forget about the mass term. Everything has a time derivative, and the solution is simply A equals a constant. And then that's going to remain true until Hubble temperature drops such that Hubble is comparable to the mass. And after this point, we're going to look like the solution looks like a damped harmonic oscillator. It's oscillating at the frequency of the mass and slowly redshifting in temperature. And after the field begins to oscillate, the coherent fluctuations of the axion field behave like cold dark matter. That doesn't mean necessarily that you get the correct abundance of dark matter. For that, you have to carry out this calculation. And you'll find you get the correct abundance of dark matter for a decay constant of about 10 to the 12 GeV for an order 1 value of this initial misalignment angle. However, this story is only true if the axion is generated before inflation, because then it makes sense to talk about a single initial value for this misalignment angle, because inflation does what it does best. It creates homogeneous initial conditions. If the axion is generated after inflation, every Hubble patch has a different initial misalignment angle. You can't neglect the spatial gradients. You can't linearize the equations of motion, which I also did, and it's much more complicated. And simulating that scenario has been a focus of mine over the past few years, but that's a subject of another talk. Okay, what I want to focus on today is searching for axion dark matter with neutron stars, and this is some work that's kind of come out of a few papers in my group over the past few years, and one reason I think that this line of papers is kind of nice to illustrate in a talk is that it has this very nice loop that we can follow, where we start from kind of pencil and paper level theoretical ideas. We get some idea that seems to work. We then go on and do simulations. Those simulations then make precise predictions that we can take data and use to interpret data. And that data comes back and and then informs the theory. So we're going to see this whole loop kind of play out for this project. I just want to highlight, I'm going to highlight throughout this talk some of the younger people involved here. Josh Foster is my grad student at Michigan. He's moving on to a postdoc next year at MIT, who is involved in a lot of this work. And then Ji-Chen Soon was an undergrad at Michigan when she did much of this work, and she's now a graduate student at MIT. Okay, so now let me orient you where we're going to be living in the axion parameter space. So what I'm showing you here is a plot of the axion parameter space of mass as a function of the coupling to photons in units of inverse GeV. So the Qcd axion should live within this yellow band, because for the Qcd axion, the axion photon coupling is proportional to the mass. So up to model dependence, we live within that yellow band. And there are certain parts of that band that are preferred. For example, from our simulations and simulations of other groups that have looked at the axion generated after inflation, we find, and others find, that the dark matter abundance, you get the corrected dark matter abundance for masses which live roughly within that blue space. So that's an interesting region to try to go after. Another region of parameter space that you might want to go after would be a gut scale Qcd axion. So axions where the decay constant is at the scale of your unification. And that's another very interesting region to try to go after. If you're not talking about the Qcd axion, you can live within the rest of this white space here. And indeed, when you look at string theory constructions, what one often finds is a large number of axion-like particles, say n of them, one linear combination will couple to Qcd. That's what you define as your Qcd axion. But you're left with n-1 axion-like particles, which still, for example, couple to electromagnetism, but they don't couple to Qcd. And so they don't have these Qcd-induced masses. And those can live anywhere in this parameter space. And in particular, on kind of the ultralight end and pushing down the smaller axion-photon couplings is a very interesting range to be looking at to try to discover these particles. So in this talk, I'm going to be focusing on these constraints here shown in green. These constraints in green came from neutron star observations that I'll be telling you about, and I'll try to motivate that the future of these searches could potentially push down far enough to probe this very well motivated part of the parameter space. Just to point out a few of the other things in this, a few of the other constraints on this parameter space. The star cluster limit here was a limit that was led by my grad student, Chris Desert at Michigan, which is also the subject of another talk using data from NuStar. And that's something that also has some potential to push down. And then Abracadabra, this is a laboratory experiment based off of a theoretical paper of mine and my collaborators. We have an ambitious experimental program. We actually just took and finished analyzing more data. So this result should be coming out soon, where we increase our constraints. And we've teamed up with the dark matter radio collaboration nearby at SLAC to form a big collaboration. We got funding from the DOE, and we're planning to push down a lot. Luckily, we scale very well with volume. So we're planning an experiment that will cover this parameter space while thinking ahead to a slightly bigger experiment that would actually get to the Qcd axion over some mass range. And then we're also thinking ahead to a multimeter experiment, which we call DM radio gut, which would be able to probe Qcd axion at kind of its most motivated gut scale parameter space. Okay, but now let me start talking more specifically about this story of looking for axions with neutron stars. So first, why are we talking about neutron stars? The reason we're talking about neutron stars is, as I'll explain to you, axions like to convert to photons in the presence of magnetic fields. And neutron stars have the largest stable magnetic fields that we know about in the universe. So they're a great place to look. So what can happen then? You can have your axions as dark matter, non-relativistic dark matter, fall in by the gravitational potential to the neutron star, hit these magnetic fields, and be converted to photons. And since the dark matter is non-relativistic, the radio signal that we're going to get at, or the signal we're going to get out, is going to sit in the radio band, as we'll see, and it's going to be roughly monochromatic, since all of that rest energy of the axion was converted into the frequency of the photon. Just as an aside, there's a very similar search that you can do where you look, instead of axion dark matter falling into the magnetic fields, you look for axions produced thermally within the core of the neutron star, which then convert to photons in the magnetic field. There you're getting an X-ray signature, and it'll be broad spectrum because they're not non-relativistic axions. That's also a very interesting signal to try to look at. That's one that we've been looking at in my group with XMM Newton and Chandra data. And we actually found an excess of hard X-rays recently from some nearby neutron stars, which seemed like it maybe could be consistent with an axion scenario. But again, that would be the subject of another talk, but just to say that there's more physics you can do with these neutron stars. But all of these processes at a fundamental level use the fact that axions can convert to photons in the presence of magnetic field. So how does this work? We have our axion, which comes in, hits an external magnetic field, rotates into a photon. So what's the conversion probability for this process? It's going to need to scale like g squared, there's a g in the Lagrangian, b squared, because there's a b in the Lagrangian. And then just to make up the units of length, the correct units, there needs to be something with units of length squared. And what is the length going to be? It's going to be some function of everything in your problem with units of length, which could be, for example, the Axion wavelength, a geometry factor for that external magnetic field, the Axion energy also would have units of, be related to units of length. And so the difference between different experiments tends to just be the difference of what is it that you take for this length parameter. So it's interesting to go and then like just look at one of these experiments and see what the length parameter is. So let's go look at the CAST experiment. So CAST is the Cern Axion Solar Telescope. It's an experiment located at Cern. It looks at relativistic axions coming from the sun and then converting in the high magnetic fields of the CAST experiment into X-ray photons, which are picked up with X-ray optics. So what's L in this case? So it's a bit of a non-trivial question because the axion and the photon will have the same energy, but there's going to be a momentum mismatch, which is going to cause the two waves to go out of phase. And that momentum mismatch comes from the fact the axion has a mass and the photon doesn't have a mass. So for the low mass limit, we don't even notice this momentum mismatch, and the relevant length scale to take for this conversion probability is the length of the CAST experiment. And we're happy about that because that's the biggest length scale we have in the problem. But as you increase the axion mass, you start to notice this momentum mismatch. And then it turns out the relevant length scale to take is the inverse momentum mismatch scale. And now we start to become sad because now the conversion probability becomes suppressed as we go to increasingly high axion masses. So now let's go back and look at this CAST constraint plot and we can understand its shape. At low masses, you don't even notice that the axion has a mass and the limit is flat. And as we go to higher masses, the conversion probability starts to become suppressed and the limit falls off. So then you might be wondering, what is going on here? Why is this limit all jagged? And it's because the CAST experimentalists are clever people. They know about this. So they try to fix it. And how do they fix it? They give the photon a mass. They put a gas within the beam pipe and they adjust the pressure of that gas to give the photon an effective mass. And then they can match the dispersion relations, but they can't do this perfectly. And they have to do a scanning strategy to implement this, which is why the limits are so jagged. So that physics right there is going to be extremely important when I now go to the neutron star story. And that's because there's also a plasma which surrounds neutron stars, which gives the photon an effective mass. And there's more plasma towards the surface of the neutron star, which means that the photon mass is going to rise monotonically as we approach the surface. So here's the picture. We have our dark matter, starts out far from the neutron star, it falls in towards the neutron star, and it's going to reach what we call the conversion radius. And at the conversion radius, the photon mass will equal the axion mass. And there will exist a conversion radius because the photon mass is rising monotonically. Here we're going to have resonant conversion of axions to photons. What does resonant conversion mean? Again, the relevant question to ask is what is the length scale for the conversion probability? In the non-resonant case, it turns out the relevant length scale is the axion wavelength, which is small. It could be centimeters or smaller. But in the resonant case, it turns out the relevant length scale to take, as I'll derive for you in a few slides, is the geometric mean of the axion wavelength and the size of the conversion radius, which is roughly the size of the neutron star, which is about 10 kilometers. So we can enhance the conversion probability by many orders of magnitude. And then radiating off of here, we get radio waves, which we can try to detect with our radio telescopes. So this effect might sound familiar to you. It might sound like MSW neutrino mixing within the sun. And there are similarities to the MSW effect, but also important differences. And the most important difference between this phenomena that I'm describing to you and the MSW effect is that in the sun, the mixing is adiabatic between the electron and the muon neutrino as a function of the electron number density, whereas the mixing that I'm going to be talking about is non-adiabatic. So why is this important? This is important because the adiabatic theorem tells us that if we're in the adiabatic regime, which is a regime of strong mixing, where in this case, the axion and photon would be mixing fast enough such that that's the fastest scale in the problem. So if you're in the adiabatic regime, what would happen? We throw in an axion asymptotically far away. It's in an eigenstate of the Hamiltonian, an instantaneous Hamiltonian. And the adiabatic theorem tells us that that eigenstate, we're going to stay in that eigenstate, and it's just going to evolve adiabatically. As it goes into the neutron star, it'll convert into partially a photon. It's going to undergo some complicated dynamics. But the adiabatic theorem says you just track these instantaneous eigenstates, which means that by the time we exit the neutron star, we would need to be back within the pure axion eigenstate. So all we would do in the adiabatic regime would be to throw in a neutron star, throw in an axion to the neutron star, and then it would just reflect off as an axion. We actually wouldn't get out a photon. But luckily, we're not in the adiabatic regime. So what happens is our axion falls in, it's very weakly coupled to the photon. It's going to cross through this conversion radius and generate a small electromagnetic wave, which will then propagate back out. But most of the axions will actually just continue through the neutron star. And then on their way out the other side, they'll have a second chance to make converted photons. Okay, so let's go through this a little bit more precisely. So I'm going to denote the axion field by lowercase a, the photon field by uppercase A, where by the photon field, I mean the component of the vector potential polarized parallel to the magnetic field. And I'm going to decompose a fast varying component from a slowly varying amplitude. So everything which is slowly varying, I've given a tilde. K here is the momentum of the axion, which is roughly ma times the velocity of the dark matter crossing the conversion surface. So then it's convenient to make a Wkv approximation, which is this slow amplitude change approximation. That is, I'm going to assume that the amplitude of this photon wave is going to change over a scale much longer than this inverse k. So what I'm denoting here is the conversion radius, and I'm going to assume that this conversion process takes place over some length scale L. So to leading order, since I'm in the non-adiabatic limit, my axion field is just completely, it doesn't notice, it's not depleted by this conversion process. So it just goes through unchanged at some initial amplitude A0. But over this length scale L around the conversion radius, I'm going to slowly build up an amplitude for A tilde. And then it's going to be frozen in roughly after this length scale L. So in this Wkv approximation, you can reduce the originally second order differential equations describing this mixing to first order Schrodinger type equations where you have some mixing Hamiltonian. The Hamiltonian looks like the following. So on the diagonals, you have a difference essentially between the axion mass and the plasma mass squared. So when the plasma mass equals the axion mass, that's when you get this resonant conversion. Then you have maximal mixing, and the mixing is controlled by the magnitude of the terms on the off diagonals. There's delta B. This delta B is proportional to the magnetic field in Ga gamma gamma, and you can interpret it as the inverse oscillation length at resonance. That is, if we're at resonance, it would take a distance inverse delta B to take the axion and fully convert it into a photon. But since we're in the non-adiabatic regime, that's not going to happen. We're only going to be able to partially convert this axion field into a photon. So the length scale L here, over which the resonant region takes place, is going to be much smaller than delta B inverse. So at this point, you just have to do the calculation. You have to solve this mixing. I'm going to skip over those details. It is convenient to solve this by mapping this problem to a problem in time-dependent perturbation theory and quantum mechanics. And then you can work this out analytically, and you find that the conversion probability scales like delta B squared over delta gamma prime at the conversion radius. Delta gamma prime depends on how fastly the plasma mass is changing in the vicinity of the conversion radius. So to make progress here, we need to have an expression for how the plasma mass changes as a function of the distance away from the neutron star. And that's what I want to turn to now. So we can use this very nice work from Goldreich and Julian in the late 1960s, who developed an analytic model for a neutron star magnetosphere. And they developed this model by going through the following exercise. We're going to try to construct the equilibrium charge density distribution for a co-rotating magnetosphere. So let's imagine that we have one charge external to the neutron star, which is co-rotating with the neutron star. Then what's going to happen? That charge is going to experience a Lorentz force because it's moving in the presence of a magnetic field. That Lorentz force will either try to push the charge away from the neutron star or pull it to it. But the system is in equilibrium, so that can happen. So there needs to be a Coulomb force which overcomes that Lorentz force. And that Coulomb force will be generated by having a distribution of charges outside of the neutron star. So you can then solve for the charge density distribution, which cancels everywhere that Lorentz force, and that gives you the Goldreich-Julian solution, which is shown here. So omega here is the spin vector, and B is the magnetic field vector. So for a neutron star, the magnetic field is roughly dipolar, so it falls off like 1/r². So you can see the number density of charges is falling off like 1/r³. So it's rising monotonically as expected as we approach the surface of the neutron star. The plasma mass squared, which is what we need to calculate this delta gamma prime, is proportional to the number density of charges over the electron mass. Here, we're going to make an assumption. So this is going to be a key assumption that I'm going to make. So I just want to flag it. I'm going to assume that the number density of electrons is equal to the number density of charges. So where would this break down? This would break down if you had a large symmetric component. If I had a large number of E plus E minus pairs, the Goldreich-Julian says nothing about those E plus E minus pairs. It only talks about the asymmetry between E plus and E minus. So in equating the number density of electrons with the charge density, I'm assuming implicitly that there are not a large number of E plus E minus pairs. And so you can ask, where would this break down? Well, it turns out that neutron stars do produce E plus E minus pairs. They produce them in pulsar jets, produce E plus E minus pairs. But I have two things to say about this. One, in this talk, we're not going to be interested in pulsars for the most part. We'll mostly be interested in dead neutron stars, which are below the pulsar death line, which are not creating E plus E minus pairs. But then two, even for pulsars, we're mostly going to be focusing on the lobes of the neutron stars, or exclusively on the lobes, which are the closed field regions of the neutron star, where there isn't E plus E minus pair creation. So even in those neutron stars, we expect this to be a good approximation. And this is something that I verified back in 2019 by teaming up with some neutron star magnetosphere simulators and checking how good the Goldreich-Julian model is for our purposes in actual numerical simulations of magnetospheres. And what we found is that it's a pretty good approximation. The Goldreich-Julian model tends to get the scale right. When you look at simulations, there can be differences from the Goldreich-Julian model, but they tend to be order 1, and the Goldreich-Julian model tends to get the correct scale. So for the purpose of this talk, the Goldreich-Julian model is going to be a fine model to use. Okay, so now we know how the charge density falls off like 1/r³. We can go back to our conversion probability formula, and we can calculate the conversion probability. And we see it's b squared, g squared, L squared, and as advertised, L is the geometric mean of these two scales. And then in practice, if you just stick in the values of the magnetic field, the axion photon coupling that you care about, you find that this number tends to be much, much, much less than 1, which means that we're safely within this non-adiabatic regime. Any questions on this so far? Okay, so now that we know how to calculate its conversion probability, we need to go ahead and calculate the flux of photons we expect to see from this process. So the differential power is a function of, for a given solid angle, is given by the following expression. So there's a factor of 2 here. The factor of 2 is because we could convert our axions both on the way in or on the way out. There's a conversion probability formula that we just went over. The dark matter density at the conversion surface times the speed at which that dark matter is crossing the conversion surface to make a flux, an energy flux, and then a geometric factor of the conversion radius squared. So great, we have the conversion probability, we have this expression for dp d omega, so now we can calculate how much power our radio telescopes are going to see. But that's not it, that's not all we need in order to estimate the sensitivity of a telescope. The other thing that we need is we need to know how narrow is this signal in frequency space. And so that's what I want to turn to now. What is the bandwidth of the signal? So the bandwidth of this signal receives a few contributions. One contribution to the bandwidth comes from the fact that we're converting the energy of the dark matter into the energy of the electromagnetic waves. And to first order, that's just the rest mass of the axion. But the dark matter does have some kinetic energy asymptotically far away from the neutron star, which will propagate down into the energy of those photons. So that gives us some kinetic corrections to the frequency, which look like delta F over F is the asymptotic velocity of the dark matter over c squared. And putting in numbers for the Milky Way, these are numbers like 10 to the minus 6 in the relative bandwidth. So that's extremely narrow. But last year, our collaboration and some other collaborations pointed out that there's actually a bigger contribution to the relative bandwidth of the signal, which comes from reflecting or refracting off of a moving plasma. So the example here is, imagine you have a tennis ball and you throw the tennis ball at a car, at a moving car. What's going to happen? The tennis ball is going to come back at you with more energy than when you threw it. Or the less violent version of this is you hit a tennis ball with a tennis racket and the tennis ball speeds up. So something very similar is happening for axion photon conversion. Because if you look at the conversion surface, we're looking down the neutron star and we look at a slice of the conversion surface is moving because it's co-rotating with the neutron star. And so we can have our axions, say, which come in and reflect off into photons. Those photons are going to be reflecting off of a moving conversion surface, which will have some component of its velocity perpendicular to the conversion surface, although that's suppressed by some geometric factors. So that photon is going to get a boost because of this conversion surface moving at some finite speed. And so this produces a contribution to delta F over F, which looks like the speed of the conversion surface times some geometric factors, which have to do with what exactly is the eccentricity of this conversion surface. And so putting in numbers for neutron stars that we care about, this number can be about 5 times 10 to the minus 6. Although it depends on a bunch of factors like what's the mass of your dark matter, and what's the magnetic field of your neutron star, and so forth. But this factor can dominate over the bandwidth, over the kinetic energy part. Okay, so now we know everything we need to calculate the signal. So now we're going to change gears a little bit, and we're going to start asking questions like, where should we look? So there are two answers to that question that I've come up with, at least, where to look. One answer is just look at nearby isolated neutron stars, like the neutron stars we were looking at in X-rays. And the reason is, for nearby isolated neutron stars, they're nearby, so the flux is not very diluted with distance. And since they're nearby, we can understand their properties quite well. And that's one approach you could take. But an alternative approach that you could take would be to look somewhere where there's a lot of neutron stars, because all neutron stars should roughly be producing flux at the same frequency. And if you look at some place like the galactic center, there's a lot of dark matter, which also enhances the flux. So that's exactly what we did in 2020. So we had an observational campaign dedicated to looking for this signal with the Green Bank telescope in West Virginia and the Effelsberg telescope in Germany. With GBT, we looked at nearby isolated neutron stars, and with Effelsberg, we looked at the galactic center. And so I want to tell you about those results now. So first, what do we do? What we do is we collect data. And what does that mean? That means we observe in different frequency bands, we observe flux values. And what are we looking for in this data? We're looking for excess flux at a frequency which corresponds to the axion mass. So then how do we do that? What we do is we first take data at extremely high frequency resolution. We then downband that data such that our signal would be expected to appear only within a single frequency band. But we don't know which frequency band. So then for a given frequency band, we perform a profile likelihood analysis, which is what I'm going to illustrate here. So we have a profile likelihood where we describe the data, which is the flux densities, as a function of the frequency band k, by a model. And that model is going to have a continuum component, which I'm denoting here by mu. We use a quadratic background, which has associated nuisance parameters, which we're going to profile over. And then a signal component, which only contributes in one frequency band. And A here, which I'm illustrating down here on this x-axis, is the amplitude of the flux within that signal band. And then the likelihood has a variance parameter, sigma squared. We treat that variance as a hyperparameter, which we learn in some sense by looking at the data on the sidebands. So then we construct profile likelihood. That is, we compute the value of the likelihood, profiling over our nuisance parameters for different fixed values of the signal flux amplitude. And so I'm just going to go through that process here. And so you just keep track of how this amplitude is changing, and then what happens to delta chi squared. So we go down, Oh, this is getting stuck. Apparently my bandwidth doesn't like this simulation, but you can see that this line is going up, and then we find some best fit value, and we find a 1 sigma and 2 sigma band for the uncertainties. So this is fine to do at 1 frequency band, but the difficulty is we need to do this millions of times because we don't know which frequency this signal is appearing at. And so to do this, it's very convenient that we have both on-source data and off-source data. So what we did was we, for example, took data at the galactic center, but we rapidly rotated the telescope from on-source to off-source, back to on-source, back to off-source. And we require a real signal to only appear in on and not in both on and off. And this is important because it vetoes RFI, which is radio frequency interference, which are things like your microwave, which creates narrow radio lines, or telecommunications satellites, which also create narrow radio lines. So I'm illustrating here the importance of having this off vetoes. So this is a survival fraction of test statistic values or delta chi-squared values on the x-axis. The way to read these plots is for a given value on the x-axis of delta chi-squared, their survival fraction tells you the fraction of mass points tested which have a delta chi-squared value at or above the value indicated on the x-axis. So under the null hypothesis, this is a very quickly dropping function because we don't see very many high delta chi-squared values under the null hypothesis from statistical fluctuations alone. So deviations away from this black curve telling you that there's something going on in the data which doesn't look like the null hypothesis. So when we have the on data only, we see a huge number of large delta chi-squared values, which tells us there are axions all over the place. We've found thousands of axions. Of course, that's not what we think is going on. We think we found thousands of microwaves and thousands of telecommunication satellites. So what we do is we then apply our off vetoes. We require a real signal to be in the on data, but not in the off data. And after we apply those off vetoes, everything falls in line and the data becomes described by the null hypothesis. So now we didn't find any evidence for an axion signal, so we can go and see how do our upper limits look like on the axion photon mass versus coupling to photon parameter space. So these are the upper limits that we found from our analyses of nearby isolated neutron stars. And then perhaps the more interesting ones were the results that we found from our studies with Effelsberg of the galactic center. And so here's our upper limit, 95% upper limit that we found from that analysis. And there are some sources of systematic uncertainty that I'm just glossing over because of time. I'm happy to go into them more afterwards. But for example, I had to assume a dark matter profile for the galactic center region, and I assumed an NFW dark matter profile. But that's certainly one source of systematic uncertainty on that analysis. And by the way, this was only 1 hour, roughly 1 hour of observation time. Okay, so what are we doing in the future? One of the reasons I wanted to tell you about this today is that I think it has a very exciting future. So I'm going to just concentrate on 2 different avenues for the future of this search. One is SKA, which is way in the future, and the other is something which is going on right now, which I'll tell you about next, which is using archival data from the SETI project. So this is something I discovered when I moved out to Berkeley, which is there's a SETI center. This is a Breakthrough Listen project, and they have acquired 20% of the time on Green Bank, the Green Bank telescope since 2016. So what are they doing? They're trying to find extraterrestrial life. How are they trying to find extraterrestrial life? Well, if you've seen the movie E.T., you know that E.T. tries to call home. And so what does E.T. do when E.T. tries to call home? E.T. emits a radio signal that's narrow band. And so what they're looking for with Green Bank and other radio telescopes is they're looking for narrow frequency radio signals. And they've pointed their telescope at the galactic center simply because there's a lot of stars at the galactic center. And they have a dedicated backend which is dedicated for these sorts of searches, but their signal looks essentially the same as our signal. So all of this archival data they've collected since 2016 can in principle be used to look for axions. So since I got here, I teamed up with that collaboration and we've started looking at their data. to look for signatures of Axion. So here is a projection of our sensitivity from an analysis that we're doing currently, which uses a tiny fraction of their available data. It only uses 8 hours of their data. There's a lot more data that they have and they will be collecting. But you can already see with a subset of the data, we're going to have very good sensitivity. This isn't an actual limit. This is a projection of our upper limit, shown here in black. We could potentially discover dark matter all the way down at this red band here, depending on how various sources of systematic uncertainty fall. For example, what is the dark matter profile at the galactic center? Does it have a bit of a cusp? And what is exactly the neutron star population model? How many neutron stars are there of different magnetic fields? So kind of most optimistically, we could detect axions down here at this red curve. Most pessimistically, we'd be able to set this upper limit shown up here at the top. There also is one magnetar, which happens to be in the field of view of this data that they took. And if we interpret the data in the context of the magnetar, we should get sensitivity that's shown here in blue, although it's less clear that that Goldreich-Julian model should apply in that case. That's a subject that needs a bit more theoretical work. So this is happening now, and this could actually stand a chance of detecting something. For example, I'll just bring your attention to this alpcogenesis band up here. This is an ALP model by Lawrence Hall and collaborators that tries to explain the dark matter abundance and the baryon abundance. And we'll be testing that model in addition to maybe touching the very top of the Qcd Axion band. And then the real improvement is going to come with SKA. Square kilometer array is a project that promises full completion by about 2030, but partial completion on timescales earlier than that. It'll have about 100 times more collecting area than GBT. It has a much larger field of view than GBT. It also has spatial information. GBT, since it's a single telescope, it only has spectra. SKA, since it's an array, it'll have both spectra and position. It's a lot more data that we can use to improve our sensitivity. This is a rough guess by how much SKA will improve our sensitivity, roughly by about 2 orders of magnitude, although that could also be more. And so at that point, I think we'll really be probing some interesting parameter space. Okay, so going to these future data sets we already see this with the SETI data, is going to require more robust statistical analysis tools. Because as you shrink your statistical uncertainties, you become more and more susceptible to sources of systematic uncertainties. And this is something that we should just be careful about going into the future if we actually want to improve the sensitivities by the amount that I'm claiming we're going to. This is something we already see with Abracadabra. So my grad student, Josh, who is the one doing these radio searches, is also the one who leads the Abracadabra data analysis. And it's because it's a very similar sort of search. We're looking for these narrow band signals in frequency space. And the issues that we deal with in Abracadabra are the same ones that we deal with in the radio telescopes, which is as you acquire more data, your error bars shrink and you become more susceptible to sources of systematic uncertainty. And this is something that we see all the time, all over astrophysical searches and laboratory searches for dark matter. For example, I had this paper last year in X-rays led by my grad student, Chris Desert. We're looking for decaying dark matter in X-rays, but it was a very similar search, essentially a bump hunt where we collected flux as a function of energy and we were looking for some signal which could be coming from decaying dark matter. And the issues that we faced there were, how do we model the background in a robust way such that we don't bias our ability to detect a real signal and we can create robust upper limits. And I just want to kind of advertise one other result that I think is pretty cool that had a bunch of students on it, just came out last week, where we teamed up with Kyle Cranmer on the ATLAS experiment to use some very modern techniques to try to make some progress here. So this is something that in ATLAS, they also, and collider searches, they also deal with, which is, for example, in Higgs to gamma gamma, you're doing a bump hunt, and you have to model that continuum background. And there are choices for how do you model that continuum background, and those choices can make a difference. So for example, in this paper by the ATLAS experiment, they modeled their continuum background by a 4th order polynomial. And so the question you should ask is, why not a 3rd order polynomial, or why not a 5th order polynomial? It seems a little bit arbitrary. So this is something that Kyle and collaborators have been thinking about in the context of experiments like ATLAS. And one technique which has been proposed is to use non-parametric modeling techniques like Gaussian processing, which also features a lot of machine learning. And the advantage of Gaussian process modeling is that you don't specify a functional form that you're fitting your for your background model. Instead, you specify more general requirements, such as what should correlations within that background model look like. So instead of specifying a function, you specify correlations. You can even learn those correlations from sideband data. So we applied this Gaussian process modeling technique to X-ray data recently, and we found that it works extremely well. And that we managed to get past some of the systematic uncertainties that were limiting us previously. And we're now taking this Gaussian process modeling and also applying it to the SETI data, because I think it's necessary, given the data volume that we have, to have a more robust background modeling framework. So that's just kind of a warning. I'm going to show you this very optimistic plot here and tell you that we could be on the precipice of discovering or ruling out the Axion, pushing down on many of these searches across the entire mass range of the Axion, radio searches, which I talked about today, but also searches across other mass ranges and searches by other groups. But to do that, we need to have robust statistical tools to be analyzing that data, such that we can actually take full advantage of the instruments that we do have. So great, that's all I wanted to tell you. And yeah, happy to clarify anything if you have any questions.
Well, thank you very much. Let's maybe unmute and clap for a very nice talk by Ben. Any questions?
How long does it take to steer the telescope from the galactic center to away from the galactic center? Isn't that like half an hour or something?
No. But it is a finite amount of time. So so it takes us about well, it's an interesting question. So first, when I said we rapidly, I use the words rapidly to describe how we move the telescope from on source to off source. We actually do this every 15 minutes. So within our, which is, I guess, rapid on these scales, but within our hour-long observation period, we'll move it a few times back and forth. But that slewing time can take up to a minute. And so when you're choosing a target on the sky to use as your off location, that's definitely something you think about, because it could be a minute over there and then a minute back. And if you only have an hour of observation time, that can start to cut down into the observation time that you had. So there are many factors that have to be considered when you're choosing that off location. You want it to be somewhere kind of near on the sky, but you don't, and you don't want it to be too far away. But you want it to be far away enough that you're not going to see a signal. And so we luckily had, it wasn't just theorists on this, we had radio astronomers on all of these collaborations who could help us optimize which off locations to look at.
Thanks.
Yeah.
I've got a question. Hi, this is Tony Tyson.
Hey.
Great talk, actually. Why not use the SETI array in California?
So there are a few, well, there are many other instruments beyond GBT that can be used in this search. In principle, any radio telescope is sensitive to what we're looking for. There are a few requirements in order to be a useful data set. What do you want? You want to have a telescope with a large collecting area. And so the most promising of kind of the current radio telescopes out there are GBT, Effelsberg, and also the VLA, because they have extremely big collecting areas. However, the difference between, say, Effelsberg and GBT and another slightly smaller telescope can be easily made up by the amount of observing time, the different observing time that those experiments were actually able to acquire. So we are working with the GBT, with the SETI collaboration to analyze data from other telescopes also. For example, there's a telescope in, I think it's in Sardinia, I want to say, the Sardinia something meter telescope. And they've acquired an absurd amount of data on that telescope towards the galactic center as part of the SETI program. And it's slightly less sensitive than the GBT telescope, but that's actually the amount of observation time that they acquired outweighs the difference of the array. So, and the same is true with VLA. So VLA is an array in the US, and they have acquired actually a lot of data dedicated for this search. Last year, there was a collaboration which took data at the Galactic Center, specifically looking for Axons. VLA is not the optimal telescope to be using because it doesn't have very good frequency resolution compared to some of these other telescopes, but they acquired so much data that it didn't even matter. They overcame that. So yeah, I mean, we're in a situation where there's literally more data than we know what to do with, and we just have to like choose one data set to start with, which is what we're doing. Yeah, we definitely plan to keep on looking at all of the archival data sets that we have available to us.
Good, thanks. And as you pointed out, time is running out because of the exponential increase in low Earth orbiting communication satellites.
Yeah, it is true. We noticed this. We can tell you based on our data when there are telescopes passing overhead, and it's yeah, it's definitely a problem for our search.
Could I ask a question? So I'd be curious to get a little more information about this. You know, your background modeling. Can you just explain what's the basic idea of why you think? I mean, if a background is unknown, it's unknown. So how are you making progress on this? Why do you think that specifying correlators or something is better than specifying a functional form? Could you say a little bit about that?
Yeah, good. So, I mean, the point is, as you say, the background is unknown. I mean, in the case of the LHC searches, you know, maybe it's unknown, but you could really figure it out if you wanted to, but you don't need to. And in our cases, in many circumstances, this is literally unknown. You have absolutely no idea what's making the background. It's some complicated convolution of astrophysics and detectors and whatever's happening in the atmosphere. But you know what your signal should look like. So for example, we know our signal and radio data should be extremely narrow in frequency space. And so now let me just tell you in words what you would like to accomplish, and then we can talk about how you're going to put that down into an algorithm on a computer. What we would like to accomplish in practice would be to look for narrow features in frequency space, marginalizing in some sense that we haven't defined yet over larger scale variations in the background model. That is, we just want to look for things which are very narrow. So that's what I want to look for. I want to look for things which are very narrow, which is the same philosophy behind, say, this Higgs to gamma-gamma search. I want to look for a very narrow feature over some continuum background. And I don't care what that continuum background's doing. I just don't want it to have correlations on very small scales. And so now I'm starting to use the language of correlation. So the advantage of using Gaussian process modeling is that I can take those words I just said and more easily translate them into algorithms. Because I can say, I don't care what the functional form is of the background model. I just don't want it to have correlations on a scale smaller than something. And then what the Gaussian process model is going to do is it's going to allow the background model to have any functional form. So, but if that background model starts to have correlations on scales smaller than some predetermined length scale, then it's going to start to penalize the likelihood function. So why is this an advantage over using functional methods? Because for functional methods, you only have the ability to be constrained within the functional form that you tell the algorithm. And so it's possible, especially if you're scanning over millions of different mass points, that you really needed a third order polynomial there instead of a second order polynomial. But it doesn't matter. If you were to look at it by eye, it'd be clear that that polynomial has correlations longer than the length scale that you care about. But your algorithm could then be fooled into thinking there's actually a signal there because it wanted that extra term in the polynomial. So, if we could go through and inspect all of these cases by eye, it would maybe be less of a big deal. But since we're dealing with millions of data points, we can inspect all of these by eye. So we need an analysis framework which is more robust. And I think Gaussian process modeling is a step in that direction. Although Gaussian process modeling still has assumptions baked into it. It assumes the correlations are the covariance. It assumes all the data can be described by some covariance matrix. And so there are Gaussianity assumptions that are baked into it. So I'm not saying that that's the end of the line, but I think it's a step in the right direction. At least we have seen it more robustly handle different variations in the background model.
Okay. Any other questions for Ben?
Maybe I can ask a very naive question. So you are basically this Axon dark matter. What about the Axon like the particle, but is not dark matter? Can you comment on the sensitivity?
Yeah. So if the for this radio search, if the axion is not dark matter, then you're not going to see a signal. Or more precisely, if the axion is not dark matter, then the signal is going to be decreased by the dark matter density that particle has. So it could be some subcomponent of the dark matter, and then everything just scales linearly. So in that sense, we're really looking here for axions as dark matter. With that said, I did mention, kind of as an aside, that there is this other very closely related search. Get back there, where we look for axion-like particles, in this case produced within the neutron star, which convert to X-rays in the magnetic field. And for this search, the axion-like particles don't have to constitute dark matter. Our signal doesn't care if they're dark matter because we're producing them. So there's two different kind of searches going on here. There's the dark matter one, which I talked about, where the axion does need to be the dark matter. We don't see anything. But there's a very closely related second search you could do that we have been doing, where the axions are not dark matter.
Okay, thank you.
Yep.
Any other questions? So let's end the official part of the seminar here, but hopefully Ben will be able to stick around and we can continue some discussions. So thanks again, Ben.
Okay. Thank you.